Hi everyone, so today I have a very nice and elegant polynomial equation for you, and we are going to see how maybe induction, the process of mathematical induction, can help us to solve that, right? So yeah, let's see how that goes. This is the problem number 4 from the Baltic Way exam in the year 2010, and the Baltic Way is basically an Olympiad between some of the Baltic nations such as Latvia, Lithuania, Estonia, and so on. And in this video, we're going to be looking at polynomial equations, how we can maybe prove certain results using induction, the induction hypothesis, and so on. After that, we have some book sessions on National Math Olympiads, and at the end, a similar challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so the goal is to find all polynomials p of x with real coefficients such that it satisfies this given polynomial equation, right? X minus 2010 times p of x plus 67 is x times p of x. Okay, great. Well, what do I see over here? I see like a bunch of variables and the polynomial p. But I also see this 67 and 2010. Now 2010 is the year in which this problem was posted for the exam. But I want to kind of maybe see some relationship between 67 and 2010. And it so happens that 2010 divided by 67 is actually 30. So 2010 is 67 times 30. And that can be an interesting result that we will see in the future. Maybe it will be helpful. Who knows? So this is like the first thing that comes to my mind. And beyond this, what I will try to do is I'll try to see, what is P of 67. I'll try to see what is P of 2010. And P of 2010 just so happens to be P of 67 times 30. Right? What is P of 67 times 2? Because you have 67 times 1, 67 times 2, 67 times 30, P 2010. Let's just kind of explore this, right? So we have this equation x minus 2010 times p of x plus 67 is equal to x times p of x. Okay, great. Let's just plug in x equals to 0, the standard substitution strategy. You will get 0 on the right hand side, right? And here you will get negative 2010 times p of 67. That essentially implies that p of 67 is equal to 0. Excellent. Okay, great. Now let's just plug in x equals to 2010. This time we get 0 on the left hand side. On the right hand side you'll get 2010 times p of 2010. So p of 2010 is 0, which naturally implies that p of 67 times 30 is 0. So we note that p of 67 is 0. So p of 67 times 1 is 0. P of 67 times 30 or p of 2010 is 0. What about p of 67 times 2? What about this, like I was referring to earlier? What about p of 67 times 3? What about these things? And how can we maybe find out, let's say, this thing? How can we find out this thing? And the answer is pretty simple. Just plug in x equal to 67. So, well, you plugged in x equal to 0. You plugged in x equal to 2010. Might as well do some justice to the problem and plug in x equal to 67. Right? And once you do that, you get 67 minus 2010 times p of 67 plus 67, that is 2 times 67, is equal to 67 times p of 67. You know that p of 67 is 0. So 67 minus 2010 times p of 2 times 67 is 0. Essentially implies that p of 2 times 67 is 0. So what do we have till now? P of 67 I know is 0. I know that p of 2 times 67 is 0. I know that p of 30 times 67, which is p of 2010, is also 0. So let me just make a claim. My claim is that for all n that belong to 1 to 30, p of 67 times n is 0. Essentially, I'm trying to say that p of 67x is 0. And how do I prove that? Induction, right? Well, the proof is going to be a proof via induction. Okay. So we're going to use the technique of mathematical induction to prove this. Now, how do you do by induction? So you take a base case, right? Base case is where n is equal to 1 and p of 67. Is it 0? Yes. So we see that the base case works, and we've already checked the base case, which is p of 67, and we know for a fact that it is 0. Okay, great. What next? So now comes the induction hypothesis, right? Induction hypothesis. What is the induction hypothesis? So suppose that for k that belongs to 1 to 29, and it's to be noted that n and k are integers. Okay, let me just note n comma k are integers. Let me just note that. And so induction hypothesis is suppose that for k belonging to 1 to 29, p of 67 times k is equal to 0. So this is again suppose, okay, consider, and now we need to prove that p of 67 times k plus 1 is equal to 0. So if we are able to prove this, that means our induction hypothesis is true. In other words, what our claim is essentially true. So we need to prove this statement. And in general, whenever you're induction, what do you do in induction? You take a base case. Usually that is n is equal to 1. Usually. Okay. Then you have what we call as an induction hypothesis, right? Where you hypothesize something, where you claim something in a way, or you assert something, you suppose something. And then this is essentially for k, and then prove that k plus 1 holds, right? So you prove for n is equal to 1, you prove that, which is the base case, n is equal to k, you like suppose that, and again n is equal to k plus 1, you again prove that. So over here we have suppose that for k belong to 1 to 29, p of 67 times k is equal to 0. And we need to prove that p of 67 times k plus 1 is equal to 0. That's what we have to prove. And how do we really prove that? Well, it's pretty simple. We just plug in x equal to 67k into our original equation. And when I do that, I'll get 67k minus 2010. I'll get p of 67 plus 67k is equal to x times p of x. So this is this times p of 67k. Now, according to my induction hypothesis, p of 67 times k is equal to 0. So it so happens that 67 times k minus 2010 times p of 67 times k plus 1 is equal to 0. And obviously this is some kind of an integer, so it will never be 0. So this has to be 0. So which implies that p of 67 times k plus 1 is equal to 0. So we had supposed that it holds for k, and we have proven that it holds for k plus 1. Therefore, our induction is true, or it's logical, and therefore the claim is true essentially. The claim that we had made that p of 67 times n is 0 for all n belonging to 1 to 30. And this is essentially true, right? So what can we deduce about the polynomial in the question? So well, what does this information mean? This information that we have conjectured over here, let me just label as equation number 2. Probably I use something else, number 1 above. So we know that p of 67 times 1 is 0. We know that p of 67 times 2 is 0. And this holds all the way up to p of 67 times 30, which is p of 2010. All is 0. So I can essentially write p of x as some combination of these things, right? I can write this as x minus 67, x minus 2 times 67, times x minus 3 times 67, all the way up till x minus 30 times 67. And let me just write this as r of x times r of x, some other polynomial r of x. Okay, great. Now what do? I plug this equation number 3 into our original polynomial equation, which was x minus 2010 times p of x plus 67 is x times p of x. And once I do that, well, what is p of x plus 67? It's nothing but x times x minus 1 times 67 times x minus 2 times 67, and it goes all the way up to x minus 29 times 67 times r of x plus 67, right? So it looks something similar to this. And once I maybe plug this into the original functional equation, I'll get x minus 2010 is equal to times this x times x minus 67, x minus 2 times 67, all the way up till x minus 29 times 67, time this quantity r of x plus 67, this is equal to x times p of x, which is x minus 67, x minus 2 times 67, all the way up till x minus 30 times 67 times r of x. So you actually see a lot of terms gets cancelled out, this and this, this and this, this and this. And so it so happens that everything, anything and everything up till x minus 29 times 67 gets cancelled out. So what we have left is this x minus 2010 term times r of x plus 67. On the right hand side, we have x minus 30 times 67 times r of x. And well, x minus 30 times 67 is the same as x minus 2010, because 2010 is nothing but 30 times 67. So it so happens that this r of x is equal to r of x plus 67, and now it should be pretty clear that r of x is nothing but r of x plus k. It's in a way a periodic function, so therefore r of x is a constant. And this is a pretty standard result. Whenever a polynomial at x, r of x is equal to r of x plus k, that means that it has to be a constant polynomial. So what's p of x? P of x was nothing but x minus 67, x minus 2 times 67, all the way up till x minus 30 times 67 times this quantity r of x, right? Let me just remind you, it was this equation number 3, right? That was what was p of x. And now we know that r of x is equal to c. So therefore, p of x is nothing but x minus 67, x minus 2 times 67, all the way up till x minus 30 times 67. Or let me just label that as 2010. And we have this c multiplied to it as well. And yes, that essentially finishes our problem. So p of x is this weird expression. It's not a very clean expression, but this is what you will get, and it's pretty clear to see that this will have 30 roots, right? 30 zeros. So yeah, I hope you learned something interesting from that. Okay, so moving on, we have certain book suggestions for National Math Olympiads: Elementary Number Theory by David Burton, Problem Solving Strategies by Arthur and Gell, Functional Equations by Venkatachala, Problems in Plane Geometry by Sharigan, Elementary Number Theory by Sierpinski, Graph Theory by Harari, and Combinatorics by Brualdi. So at the end, we have a similar but challenging problem, and this is again a polynomial equation. And I wanted to find all polynomials p of x with real coefficients so that it satisfies this given polynomial equation. One observation is that x minus 1 times x plus 1 is actually equal to x square minus 1. Maybe use that hint. Maybe try to see how you can use that in the solution and try this out and let me know how it goes. I'll probably be covering this particular equation in one of the future videos, because it is a problem from the IMO long list, so it's probably worth discussing. And until then, I'll see you in the next video. Thank you very much, and bye-bye.
The programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.